In this video, I'll talk through the Higher Chemistry Unit 2 topic of soaps, detergents and emulsions. By the end of this video, you should be able to describe how soaps are made, be able to explain the cleaning action of soaps and detergents, be able to describe how emulsifiers are produced and how they work. Starting off with soaps, soaps are made by the alkaline hydrolysis of fats and oils. The alkalis that are most commonly used would be sodium and potassium hydroxide. Another term used is saponification. In this case, we have a fat on the left-hand side. We are reacting it with the ionic sodium hydroxide. The ester links are broken up and we form glycerol and fatty acids. Those fatty acids then react with the alkali, producing ionic salts called soaps. A way of recognising the soap molecules is you're looking for something that looks very similar to the C-double-bond-OH of a carboxylic acid, but we've replaced the hydrogen with a metal ion. We make 3 molecules of soap for every 1 molecule of glycerol, in the same way as that making fats and oils, we have 1 glycerol and 3 fatty acids join on to it. The purpose of soap is to help remove non-polar substances like oil and grease from a surface. Constructed of 2 parts, we have our ionic water-soluble head. A word that comes up often is hydrophilic. It's able to dissolve in the water. We can have them represented as a straight chain hydrocarbon as in the first one, and the second one is showing a skeletal form where each change in direction represents a carbon. So these 2 are the same molecule. When dealing with the tail is non-polar and oil soluble, and the word we can use for this would be hydrophobic. When soaps are used to clean, 2 things happen. The heads will dissolve in water and the tails will dissolve in the oil or grease. When the mixture is agitated, so as if you're scrubbing it or shaking it, the grease or oil breaks up into small ball-like structures described as being micelles or micelles. When we have little droplets suspended in the water, that's described as being an emulsion. Next, getting to probably my favourite word of the whole entire chemistry course, and maybe even all of the SQ chemistry courses, scum. Soaps can form scum in hard water areas. Hard water contains higher levels of metal ions. Examples would be calcium and magnesium. These ions react with the soap to form an insoluble precipitate. These kind of precipitates you might have heard of or seen adverts talking about getting rid of limescale from kettles, dishwashers and things like that. That doesn't tend to be a problem in most places in Scotland which have soft water. This is more of a problem in islands that have hard water supplies. Next we come to detergent. Detergents are very similar to soaps. They work in the same way. The main difference is that ionic head is now not made up of carbon. We now have a sulfur, and they do not form scum because their ionic heads do not react with calcium and magnesium, and we don't form that insoluble precipitate or scum. Next we come to emulsifiers. Emulsifiers prevent polar and non-polar liquids from separating, and they form again an emulsion. And they are made by reacting edible oils with glycerol. For example, when making a cake batter, if you have not got the right levels of emulsifier, those 2 layers will separate out and you end up with a batter or a mixture that has split. You might have seen that on things like the Bake Off and stuff like that as well. They also have polar and non-polar groups. In these examples, the polar groups are hydroxyl groups, that's the OH groups, and that means that part can dissolve in things like water, which are polar, and in the non-polar long carbon chains, C17H35 in my examples, they'll be able to dissolve in the non-polar liquids such as oil. Now we're going to look at some exam style questions covering these topics. First one is, here we have the reaction diagram. We have our fat or oil reacting with an alkali to form glycerol and fatty acids. That is an example of a hydrolysis reaction. Alkaline hydrolysis to be exact. Condensation and esterification are ways of making esters, fats, oils and proteins. Here we're splitting up. In this one we're breaking apart. In this one here we're asked about the type of reaction taking place when this acid reacts with sodium hydroxide. Acid plus alkali makes salt plus water. That is a neutralization reaction. Next one, we're asked about which of the following is the salt of a long-chain fatty acid. Salts are produced by neutralization reactions. Soaps are produced when an acid reacts with an alkali. That's going to be our answer of soap. Fats and oils are used to make soap. Glycerol is a byproduct of fats and oils producing soaps. Soap is the salt of a long-chain fatty acid. In this one, we have to pick the correct diagram and explanation for the cleaning action of soap. The heads are hydrophilic, they're ionic, they dissolve in water. The tails are hydrophobic, they're covalent, and they dissolve in the grease or the oil, which is the grey blobby part that we have. A and B have the correct diagram, where the tails go into the grease and the heads are all on the outside. We then need to read through the explanations. So hydrophobic head is incorrect, hydrophilic tail is incorrect, so A is totally ruled out. B, hydrophilic means it likes water, that makes sense. Hydrophobic tail dissolves in oil, that makes sense. That is going to mean the answer is going to be B. C, at least the explanations are the correct way around, so hydrophobic does mean it would dissolve in oil, hydrophilic in water, but the diagram there is the wrong way around. The heads would be on the outside and the tails would be on the inside for that one. So overall, B is the correct answer. In this one, we're talking about making our soap, and we're asked about how this helps keep the grease and non-polar substances suspended in the water during cleaning. We want to talk about the two parts of it. We had a head and we have a tail. The hydrophilic head dissolves in water. The hydrophobic tail dissolves in the grease. When that is agitated, so scrubbed or shaken, that causes ball-like structures, the micelles, to form, and that keeps it suspended within it. That then allows the water to be washed away, and then it will make its way through the waterworks. In this one, we're told we have an emulsifier, and we're asked why that's added to chocolate. Emulsifiers prevent polar and non-polar liquids from separating, so we're looking to talk about things like the oil and the water-based stuff. They are going to be kept mixed together. In terms of making emulsifiers need to have both polar and non-polar sections. The oils take care of the non-polar sections. Glycerol has 3 hydroxyl groups. That provides the polarity, has the hydroxyl groups to dissolve in the water-based things. In this one, we're given diagrams of different compounds and asked which of the following could act as an emulsifier. We're looking for something that has both polar and non-polar sections. It's also helpful to remember that glycerol and edible oils react together to form these things. We're looking for something that's a cross between glycerol and an edible oil. A is glycerol. It's propane 1,2,3 triol. B is a fat and oil with 3 long-chained hydrocarbons coming off of each section. C is a fatty acid, whereas D is an emulsifier because it has 2 long-chained hydrocarbon chains. It has 2 long-chain hydrocarbons and 1 hydroxyl group, meaning it can dissolve in both polar and non-polar substance, making D the correct answer for this question. That brings us to the end of the video. Hopefully by now you're more comfortable in describing how soaps are made, explaining the cleaning action of soaps and detergents, and being able to describe how emulsifiers are produced and how they work. Thanks for watching, goodbye.